to all? Hello? Hello?
Yes, sir.
Okay, the screen is visible to all. Is it?
Yes, sir.
Okay.
Yes, sir.
Yes,
So
sir.
in the last lecture, we seen that one corollary. Okay. After the main theorem, let K be the normal extension of a field F with characteristic 0, then order of GKF is equal to degree of K over F. So today we'll see one more theorem. Look at the statement. Wait a minute. Theorem. Let capital K be splitting field. Capital K be a splitting field of f of x, which is a polynomial belongs to capital F of x. Okay, and let p of x be an irreducible factor. Be an irreducible factor of f of x. Okay, be an irreducible factor of f of x in capital F of x. If the roots of p of x, if the roots of p of x are alpha 1, alpha 2, up to so on alpha r. Okay, so degree of p of x here is r. Okay, so there here r roots are there, so the degree of p of x is r. Then for each I, for each I, there exists an automorphism. There exists an automorphism sigma I in GKF, GKF such that this sigma I of alpha 1 is equal to alpha I. Okay, what is the statement? Let K be the splitting field of f of x. This f of x we can write in the form of linear factor on the field K. Okay, let P of x be the irreducible factor of f of x in capital F of x. If the roots of P of x are alpha 1, alpha 2, up to so on alpha r, that means the degree of P of x is r and all the roots are distinct roots of P of x. But P of x is irreducible over in f of x, capital F of x. Then for each I there exists an automorphism sigma I in GKF such that sigma I of alpha 1 is equal to alpha I. Okay, now look at the proof. It is given that K is the splitting field. Write down all the given things. It is given that capital K is splitting field of f of x. Splitting field of f of x. Okay, in capital F of x. This f of x is belongs to capital F of x, and p of x is an irreducible factor. Okay, irreducible factor of f of x in again capital F of x. Okay, now look at here. Since p of x is a factor of f of x. Okay, therefore every root of p of x also root of
F of x.
f of x. Okay, so every root of p of x. So every root of P of X must be in capital K. Okay, any doubt up here? Okay, now let
No, sir.
alpha 1 and alpha I be the any two root of P of X. Okay, let alpha 1 and alpha I. Alpha I is the any arbitrary root of P of X. Okay, but alpha 1 is fixed here. So let alpha 1 and alpha I be any two roots of P of X. And let here F1 is equal to adjoint alpha 1 to the field F. Okay, and give the and say that field is F1. And F1 dash is equal to F of alpha I. Okay, that arbitrary root adjoint to the field F and give name to that field is F1 dash. Okay, this is F. This is F. This one is K. Okay, all the roots are in K. Alpha 1, alpha 2, alpha 3 must be in K. Okay, this is the alpha 1, alpha 2 up to so on, alpha R. Okay, this is F. Okay, and this is F of alpha 1. Okay, and this one is K. Similarly here, this one is F. And this one is F of alpha I. And this one is K. Okay, so let here F1 is equal to this is F1 and this one is F1 dash. Okay, so since P of X belongs to capital F of X, it's irreducible. Irreducible. Therefore, therefore, by the theorem, which theorem? Look at here in the bracket. If f of x belongs to capital F of X is irreducible. Okay, and A and B are two roots of F of X. Then we've seen that in the previous lectures, this F of A is isomorphic to F of B. Okay,
F
by
of
an
B.
isomorphism. By an isomorphism which takes A onto B. Okay, A is a mapping B A onto B, and which leaves every element of X is fixed. Okay, which leaves every element of capital F is fixed. Okay, so yeah, if psi is an isomorphism of F of A into F of B, then for F psi of alpha is equal to alpha for all alpha belongs to capital F, and psi of A is equal to what? B. Okay, so this theorem we studied in the previous lectures. Okay, so here the P of X is irreducible element, irreducible polynomial. Therefore, by this theorem, we have, okay, wait a minute. There is an isomorphism. Therefore, by this theorem, there is an isomorphism. Isomorphism psi on F1 onto F1 dash. Okay, look at here. There is an isomorphism from psi onto F1 onto F1 dash. Okay, here the alpha 1 is a root. Alpha I is also root of P of X, and P of X is an irreducible polynomial. Okay, so by this theorem, there is an isomorphism psi on F1 onto F1 dash such that psi of alpha 1 root maps to roots is maps to alpha I, and psi of alpha is equal to alpha for all alpha belongs to capital F. Okay, any doubt up to here? Now, since
No, sir.
F1,
No, sir.
since F1 is subfield of, is the subfield of, sorry, superfield of, not subfield, is super field of small capital F. Okay, and this f of x belongs to capital F of x. Okay, so f of x can be considered as polynomial over f1. Okay, why? Since f is contained in f1. Okay, and f of x is the polynomial belongs to capital
F1.
F of x, then f of x. Okay, so this f of x can be considered as a polynomial over f1. Okay, now we have what we have. K is the splitting field of f of x. Okay, look at it. Hmm. We know that capital K is splitting field of f of x belongs to now f1 of x. Any doubt? Okay,
No, sir.
because no subfield of capital K containing f1, and hence, wait a minute, hence f can split f of x. Is it correct statement? Look at here. Because no subfield of K containing f1, and hence f1 f can split f of x. K पाहिजे f च्या ठिकाणी k पाहिजे काय f पाहिजे? Okay. K असायला हवा ना, because no
K
subfield
पाहिजे
of
ना,
K
sir.
containing f1, and hence K can split f of x. Okay, it's a wrong sentence. Okay, K can split f of x. Okay. Now, similarly, K is the splitting field of f of x, and consider the polynomial over f1 of x. Okay. Similarly, K is splitting field of f of x. Okay. Considered as a polynomial over f1 dash. Okay. f1. Now, f1 f is contained in what? f1 dash also. Okay, so similarly here K is the splitting field of f of x, and consider that as the polynomial over f1 dash. Okay. Now we have one theorem. Okay. What is this theorem? By the theorem, two splitting fields are isomorphic. Okay, we know that two splitting field of any polynomial are isomorphism. Okay. So by theorem. Okay, previous lecture ला पाहिलेलं theorem. By theorem, previous lecture म्हणजे आधी झालेलं आहे, खूप आधी झालेलं आहे. In the bracket, two splitting fields of same polynomial are isomorphic to each other. Two splitting fields are isomorphic. Okay, so hence, here, hence, there is an isomorphism. There is an isomorphism. There is an isomorphism sigma I, okay, of K onto itself, K onto itself, coinciding, coinciding with psi on F1. Okay, it is part. There is an isomorphism from on K. Okay, splitting field on K. Okay, this is the sigma I. Okay, which leaves every element of continuation of isomorphism theorem. Okay, if K is the splitting field of this polynomial over F1, and again here the K is the splitting field of polynomial over F1 dash, then that two splitting fields are isomorphism. Okay, so here the domain and codomain is same, so there exists an automorphism sigma I, which coincide with psi on F1 and F1 dash. Okay, on F1. Look at K. So there is an isomorphism sigma I on K onto itself, coinciding with psi on F1. Okay, so now if alpha 1 belongs to f of alpha 1, which is equal to f1, this implies sigma I of alpha 1 is equal to psi of sigma कोणाला coincide psi ला coincide. Okay, sigma आणि psi आहे equal असेल कोणावर f1. Okay, which is equal to sigma 1. Sorry, psi of alpha 1, which is equal to, but psi of alpha 1 is what? Alpha I. Okay, any doubt? Any doubt? हे थेरम आपण मागच्या लेक्चरला आपण
No,
फर्स्ट
sir.
चॅप्टर मध्ये बघितलं. सिंपल एक्सटेन्शन, अल्जेब्रिक एक्सटेन्शन वगैरे त्याचे थेरम होते ना, तिथे पाहिलं झालेलं आहे. Okay, continuation of isomorphism. There exists an isomorphism on K unto itself. That is automorphism sigma I. If K is the splitting field of polynomial over F1, here the K is the splitting field of P of X, F of X. Sorry, P of X on F1 dash. Okay, so this sigma I is coincide with psi on F1. Okay, that is coincide म्हणजे काय होतोय? Sigma I of alpha 1 is equal to psi of alpha 1 is equal to, but what is psi of alpha 1? Alpha I. Okay, so also sigma I coincide on also, since this sigma I coincide with psi on F1 was the coincide of the same, so F1 minus was obviously what, because F is contained in F1. Okay, F is contained in F1. Okay, so therefore sigma I of alpha is equal to alpha, which is equal to psi of alpha for all alpha belongs to F. Is it correct? Okay, so this implies sigma I of alpha is equal to alpha for all alpha belongs to F. Okay, so this implies sigma I is element of G, K, F. Okay, F च्या प्रत्येक एलिमेंटला फिक्स करतोय म्हणजे काय होतोय, हा सिग्मा कशात जातोय? G, K, F. Is it correct? Okay,
Yes,
what is
sir.
the meaning of this one? Set of those automorphisms which on K of K, which leaves every element of F is fixed. Here the sigma of alpha is equal to alpha for all alpha belongs to F. Okay, but sigma is an automorphism on K. So this sigma I belongs to GKF by the definition of GK. Okay, so sigma I belongs to GKF and sigma I of alpha 1 is alpha I. Hence equal. Okay, so there exists an isomorphism sigma I in GKF such that sigma I of alpha 1 is equal to alpha I. This is the step. Okay, if A is the splitting field of f of x belongs to capital F of x, and let P of x be an irreducible over f of x in capital F of x. Okay, in alpha 1, alpha 2, up to so on alpha r are the roots. Then for each I, there exists an isomorphism sigma I in GKF such that sigma I of alpha 1 is equal to alpha I. Any doubt up to here? काय doubt असेल तर विचारू शकतो. Okay, याच्यानंतरचा पुढचा
No,
थेरम
sir.
त्याचा थेरमचा पुढचा आहे 7th पेज. ओके, सो नीट कॉन्सन्ट्रेट करून लक्ष द्या. ओके, थोडे तुम्हाला काही समजणार नाही. Now the next theorem. Wait a minute. Wait a minute. थेरम किमान 1 तास लागेल थेरमला, त्यामुळे नीट लक्ष द्या. If K, if field K is normal extension of a field F, if field capital K is a normal extension of a field F of characteristic 0, if and only if K is a splitting field. K is a splitting field of some polynomial over F. Okay, so this is the statement of the theorem. Okay, the proof is very lengthy, so keep the concentrate here. Okay, so a field K is the normal extension of the field F. What is the meaning of this sentence? Normal extension means the fixed field of GKF is F. Okay, with characteristic 0 here. The characteristic of F is 0. If and only if K is the splitting field of the sum polynomial over F. A काय असायला हवा तुमचा splitting field of polynomial over F. This is the F, and this one is the extension of the field F. This K is the splitting field of F if and only if there is some polynomial. Okay, there is some polynomial. Suppose this is F of x belongs to capital F of x. This F of x splits over K. Okay, then K is normal extension of F. Okay, only if part, first part 1. Only if part, or only if part. Suppose capital K is a normal extension of F. Okay, suppose capital K is the normal extension of capital F. We have to prove that K is a splitting field. K is a splitting field of some polynomial over capital F. Okay. Capital K is normal X. जेव्हा तुम्हाला डाऊट असेल त्याच वेळेला लगेच विचारायचं. असल्यामुळे एकदा पुढे गेल्यानंतर मग मागचं तुम्हाला लक्षात नाही राहणार. स्टेप बाय स्टेप समजत चाललंय का पहा. ओके, जेव्हा थेरम संपेल शिकून झाल्यानंतर पुन्हा तुम्ही रिव्हिजन करायचं. ओके, सगळ्या गोष्टी एकदम तुमच्या लक्षात नाही राहणार हा जो प्लेन दिसला. ओके, हियर look at here, as k is normal extension, so by the definition k is necessarily a finite extension of f. Okay, every normal extension is a finite extension. K is necessarily a finite extension of the field f. Okay, so as the characteristic of f, the characteristic of capital F is what? 0. Okay, here the characteristic of f is 0 and k is the finite extension of f. Then it follows by the theorem k is the simple extension. Okay, finite extension with characteristic f of 0, then k is what? Simple extension of f. Okay, so it follows by the theorem that capital K is a simple extension of f. Okay, this theorem we also proved in the previous lectures. Every finite extension with the characteristic of the base field is 0, then that extension must be a simple extension of that base field. Okay, so it follows that by the theorem k is the simple extension of f. So what is the meaning of simple extension? K is equal to f of a, where a belongs to k. Okay, so there is an element a in capital K such that k is equal to f of a. Okay, since k is finite extension of field of characteristic 0. What is the reason? Since k is finite extension of f with characteristic of f is 0, then k is equal to f of a. Okay, any doubt up here? Okay, so in the last lecture, by the
No, sir.
order of g k f is equal to degree of k over f. Okay, by the corollary, we have this one, order of g k f. ओके, मागचं झालेलं वाचत चला बरं का. एकदा मागचं पुढे गेल्यानंतर मग मागचं काही लक्षात राहत नाही, सगळे थेरमिक सारखेच वाटतात. So order of GKF is equal to degree of K over F. Okay, now suppose the group GKF. Okay, the group GKF is of order n. Okay, suppose that set contain n elements. Okay, what are the elements? Let sigma 1, sigma 2, up to so on, sigma n denotes all distinct element. Okay, distinct element in G, K, F. Okay, where sigma 1 is an identity automorphism. Okay, the group of that identity element is identity automorphism of K. Automorphism of capital K. Okay, now let's assume assumption. Let alpha 1, alpha 2, up to so on alpha n be the elementary symmetric function. Elementary symmetric function. Wait a minute. Elementary symmetric functions of the elements. What are the elements? Sigma 1 of A, sigma 2 of A, up to so on, sigma n of A. Okay, A तुमचा काय? High element. Okay, high element. Sigma 1 of A, sigma 2 of A, and all sigma n of A are belongs to कशातले element आहे ते? K ना? Sigma is an atom of K. Okay,
K.
that is, we can write alpha 1 is equal to summation of I running from 1 to n sigma I of A. And what is alpha 2? Summation I less than j sigma I of A into sigma j of A. Okay, and up to so on. Alpha n is equal to sigma 1 of A into sigma 2 of A up to so on sigma n of A. Okay, product of all these sigma. Okay, any doubt? Okay.
No, sir.
Now note that each alpha I is in the fixed field of, sorry, invariant under sigma. Okay, note that each alpha I is invariant. Each alpha I is invariant under every sigma belongs to GKF. Okay. For every sigma belongs to GK. Okay. Any doubt up to here? So sigma of alpha equal to alpha.
No,
Okay.
sir.
Now hence each alpha I is in the fixed field of GKF. Okay, if K is the normal extension of F, we assume that, look at here. In K is the normal extension of F, it means what? Fixed field of GKF is F. Okay, and each alpha I belongs to what? F. Okay. So hence each alpha I is in the fixed field of GKF, but K is normal extension of F. This implies F is fixed field of GKF. Fixed field of GKF. That implies this alpha I belongs to capital F. Okay, in the last lecture, in the previous lecture, we seen that this here the each alpha I is invariant under every sigma belongs to GK. Okay, and this alpha I belongs to what? F. म्हणजे हा alpha I, alpha कशात येतोय? This is the element from capital F. Okay, sigma I of A plus sigma 1 of A plus sigma 2 of A up to so on sigma n of A. The addition of this element goes to F. Okay, diagram लक्षात ठेवा. F is the subfield of K. F is the normal extension. K is the normal extension of F. Okay. So here, in the last lecture, in the previous theorem, we seen that alpha I is invariant under every sigma. Okay, that means sigma of alpha I काय येतोय? माझा alpha I येतोय. Okay.
Alpha.
Now, but what is k? K is the normal extension of f. That means f is the fixed field of gkf by the definition of normal extension. So this alpha I in the fixed field of gkf is mean that this alpha I belongs to capital F. Now consider the polynomial. Consider the polynomial. Which polynomial? This p of x. Assume this polynomial p of x is equal to x minus sigma 1 of a into x minus sigma 2 of a up to so on. Okay, product of all these factors. X minus sigma n of a. Give it as an equation number 1. This is the polynomial over k. Okay, all the terms belongs to what? In k na. So this polynomial belongs to k here. Now, after the multiplication of each term, we get p of x is equal to x raised to n. Okay, degree is n now. So here x raised to n minus first term is plus, second term is minus alpha 1 of x raised to n minus 1. Is it correct? Plus alpha 2 x
Yes,
raised to
sir.
n minus 2 minus up to so on plus minus 1 raised to n alpha n. And since here, look at here now, each alpha I belongs to capital F, this implies all the coefficients of this polynomial belongs to now F. So this P of x be the polynomial belongs to capital F of x. Okay. Now f of x, P of x be the polynomial over f of x, and this P of x splits over k. Okay, so from 1, okay, this is the equation. अब P of x काय होतोय तुमचा स्प्लिट होतोय कशावर k वर आणि तो पॉलिनॉमियल कुठून आलाय each coefficient belongs to f, that is P of x belongs to capital F of x. So from 1 we see that capital K splits P of x belongs to capital F of x into a product of linear factors. Okay, is it correct? And also we have sigma 1 of a is equal to what? A. Okay, why? Because sigma 1 is an identity of vector. Now sigma 1 of a is a root of p of x in capital K. Look at here. If you put instead of x sigma 1 of a, so this is the root of p of x in K. Okay, so sigma 1 of a is equal to a is the root of p of x in a. Okay, since this a generates capital K over f, that is, what is the meaning of this sentence? K is equal to f of a. Is it correct? ओके, हा जो रूट
Yes,
आहे
sir.
तो कोणाला ऍडजॉइन केला, एफ ला ऍडजॉइन केला. ओके. From 1 we see that k splits p of x belongs to capital F of x into product of linear factors. म्हणजे तो जो k आहे तो p of x ला स्प्लिट करतोय इंटू लिनियर, म्हणजे काय, लिनियर प्रोडक्ट ऑफ लिनियर फॅक्टर्स. We can write p of x into the product of linear factors, and sigma 1 of a is equal to a is the root of p of x in k. Okay, since a generates k over f. Okay, look at here. What is k? Is equal to f of a. Okay, since a generates k over f, that is k is equal to f of a. So this implies a satisfies the polynomial p of x. But p of x is what? Wait a minute. Okay, k is equal to क्या होता है f of a, and a satisfies the polynomial p of x. Okay, so look at it. This implies therefore a can be can be in no proper subfield of k, no proper subfield of k which contain f. ओके, म्हणजे के च्या आणि एफ च्या मध्ये कोणताही प्रॉपर सबफिल्ड येणार नाही. ओके, इफ यू adjoint this element to a to f, then we get k is equal to f of a. Okay, so there is k can be in no proper subfield of k. k च्या कोणत्याही proper subfield मध्ये a ही नसणार नाही which contains f. Okay, that means f of a is equal to k. Okay, so this implies thus k is a splitting field of p of x over f. Okay, so here the p of x belongs to capital F of x. Okay, with the polynomial in f of x. Sorry. Okay, which splits k splits that polynomial p of x. ओके, म्हणजे हा स्टेटमेंट घेण्याचा उद्देश काय, या f आणि k च्या मध्ये कोणताही सबफिल्ड नाहीये, कोणताही k चा सबफिल्ड नाहीये जो a ला आणि f ला कंटेन करेल. That means that k is nothing but f of x. That means this k splits the p of x, and p of x with the polynomial belongs to capital F of x. Hence the proof. Okay, so this is the part one. Any doubt? Okay.
No, sir.
Wait a minute. Now, revise. Okay, what is? Suppose k is the normal extension of f. Then we have to prove that k is the splitting field of some polynomial over f. ओके, एफ मधला असा एक कोणता तरी पॉलिनॉमियल येईल जो के वर स्प्लिट होईल, हे आपल्याला दाखवायचं. तो पॉलिनॉमियल आपण कसा तयार केलाय, टेकिंग रूट. ओके, टेकिंग दिस एलिमेंटरी सिमेट्रिक फंक्शन x minus sigma 1 of a, x minus sigma 2 of a, up to so on x minus sigma n of a, याच्यापासून एक पॉलिनॉमियल तयार केलाय ओव्हर के असेल तो. ओके, but this all now the p of x belongs to f of x. The p of x be the polynomial over f of x which splits over k, but k is what, f of a. So hence here k is the splitting field of p of x. Okay, so p of x म्हणजे काय, माझं polynomial in f of x, and over k we splits that polynomial into the linear factors over k. Okay, any doubt? Now part
No,
second.
sir.
Part 2. If part. Suppose capital K is splitting field of the polynomial f of x belongs to capital F of x. Is the splitting field of the polynomial f of x belongs to capital F of x, and we have to prove that k is normal extension of f. म्हणजे काय दाखवायचं आहे, fix the field of GKF is f. Okay, fix the field of GKF is f. That is fixed field of GKF is f. But we know that what is fixed field of f is contained in what? Fixed field of GKF. This one we know. Okay, if we prove the fixed field of G contained in capital F, then the fixed field of GKF is F. ओके, हा ह्याच्यात कंटेंट आहे आणि हा ह्याच्यात कंटेंट आहे आणि हा जर ह्याच्यामध्ये कंटेंट झाला तर काय होईल, दोघे इक्वल येईल. सो फिक्स्ड फील्ड ऑफ GKF is F, then automatic by the definition we get K is the normal extension of F. Okay, so we have to prove that the K is the normal extension of F. Okay, now the obviously K is capital K is a finite extension of F. A finite extension of F, capital F. Okay, why? Because what is the reason? Every splitting field. जो काही splitting field असेल, every splitting field is a finite extension. Okay, splitting field काढतोय म्हणजे काय करतोय? We have to find all the roots of that polynomial, and if you adjoin that roots to the base field, then we get splitting field. Okay, so here the K is the splitting field of F. That means K is nothing but what? F of alpha 1, alpha 2 up to so on alpha n. If alpha 1, alpha 2 up to so on alpha n are the roots of that polynomial. Okay, so here K is the finite extension of F, obviously. Why? Because K is the splitting field of some polynomial in f of x. Some polynomial f of x belongs to capital F of x. Okay, so here the K is finite extension of F. Now let the degree of K over F is equal to F. Okay, degree of K over F is equal to F. Now we shall prove this result by induction. Okay, up to here any doubt? Any doubt? Okay.
No, sir.
Now we shall prove the result by induction on n. Okay, first to start the induction, we see that if suppose degree of K over F is equal to 1, so this implies K is equal, okay, K is equal to
K is equal to F.
Okay, so this implies F is normal extension of capital F. Okay, so the result is true for if degree of K over F is equal to 1. Okay, in the bracket right now, that is fixed field of G F F. Okay, instead of K, write F now. It's F itself. याचा अर्थ काय? Fixed field of GFF is F itself. This means this atomorphism, the set of atomorphism. It is the set of atomorphisms of K which leaves every element of F is fixed. F वर असणारे असे atomorphism घ्या की तो F ला fixed करतोय. Okay. Suppose sigma 1, sigma 2 up to sigma n these are belongs to GKF. आता हे सिग्मा 1 सिग्मा 2 या F मधल्या कोणत्या एलिमेंटला फिक्स करतायत? F लाच ना. So the fixed field of GFF is F itself. Okay. So if K is equal to F, the result is obviously true. Okay, now assume our induction hypothesis. Doubt up to here?
No, sir.
स्टेटमेंट. ओके, ह्याच्यामध्ये काय असणार तुमचे सगळे ऑटोमॉर्फिझम. सपोज सिग्मा 1 सिग्मा 2 ते काय करणार, या एफ एलिमेंटला काय करणार, फिक्स करणार. सेट ऑफ दोज आर ऑटोमॉर्फिझम्स ऑफ एफ which leaves every element of this f is fixed. Okay, so what is the fixed field of GFF? Fixed field of GFF is means take the element A belongs to F such that sigma of A is equal to A for all A belongs to F. याचाच अर्थ काय, F is itself. Okay, हा सेट काय ना, होल सेट येणार तुमचा फिक्स्ड फील्ड. ओके, hence here we get fixed field of GFF is F itself. Now, assume that our induction hypothesis. Assume as our induction hypothesis that if K is or K1 is splitting field over F1 of a polynomial in F1 of X. Okay, and degree of K1 over F1 is less than n. Okay, for less than, we are assuming here this statement is true for the degree less than n. Then this K1 is a normal extension of F1. Okay, so this is the induction hypothesis. If K1 is the splitting field over F1 of the polynomial in F1 of X, and the degree of K1 over F1 is less than n, then the K1 is the normal extension of F1. Okay, now we have to prove that for the degree K over F is equal to n, this statement true. Okay, let degree of K over F which is equal to n, which is greater than 1. Okay, now K is splitting field over capital F of this polynomial f of x belongs to capital F of x. Okay, if this f of x splits into linear factor over f, then what we have, K is equal to F, and consequently जर तो लिनियर फॅक्टरला तुम्ही स्प्लिट होत असेल ओव्हर F1, then काय येईल माझा, K म्हणजेच माझा F येईल. ओके, that F is splitting field of that polynomial f of x. Okay, so consequently we get degree of K over F is equal to what, 1. So assume that so assume that f of x, this polynomial f of x, okay, has an irreducible factor f of x belongs to capital F of x of degree, suppose r, which is greater than 1. Okay, so f of x has an irreducible factor, sorry, p of x, not f of x. हा p of x हा कोणाचा irreducible factor आहे, हा f of x. ओके, जर इरिड्युसिबल फॅक्टर नसेल तर ते काय होईल, स्प्लिट होईल इंटू द लिनियर फॅक्टर over f. Then we get k is equal to f. So consequently, we get the degree of k over f is equal to 1. So we must have f of x has an irreducible factor p of x. Okay, and suppose the degree of p of x is r, which is greater than 1. Okay, now look at here. Since the characteristic of f is 0, since the characteristic of f is 0 and p of x is irreducible. What we get? This implies p of x cannot have multiple roots. Okay. Okay. Half theorem आपण use केला मागे पाहिजे. If characteristic of f is 0 and p of x, f of x belongs to f of x, be an irreducible polynomial, then f of x cannot have multiple roots. All the roots are distinct roots. This characteristic of f is 0. Okay. So this implies the degree of p of x is what? R. So there are R roots in K. Okay, so this p of x has all the roots in capital K. Any doubt?
No, sir.
Okay. Now let alpha 1, alpha 2 up to so on. स्टेप बाय स्टेप सगळं समजत असेल तर मग काही अवघड नाही. ओके, एकदा काय थेरम सगळं झाला की मग आपल्याला त्याचा अनालिसिस करता येईल आणि कोणत्या स्टेप नंतर काय आहे हे लक्षात येईल. ओके, आधी स्टेप्स तर समजून घ्या व्यवस्थित. लेट the degree of p of x is r and p of x has no multiple root, have a no multiple root. Suppose this alpha 1, wait a minute, alpha 2 up to so on alpha r, p are distinct root of p of x in capital K. Since p of x is what? Irreducible over f, not k. Okay, and degree of p of x is equal to r. Now this implies p of x is irreducible. Degree of p of x is equal to r. Then adjoint this alpha 1 to the base field f. Okay, so degree of f of alpha 1 over f is equal to काय r ना. Okay, why? Because this
R.
alpha 1 satisfies the polynomial p of x which is irreducible, म्हणजे तो minimal झाला over field f. So degree of f of alpha 1 over f is what? R. What is the reason? Since alpha 1 is root of p of x. Okay, so that is in the bracket right now. Alpha 1 is algebraic of degree r over f. Okay, so we have what we have, degree of k over f is equal to, by the transitivity of finite extension, we have degree of, this is f, this is f of alpha 1 and this one is k now. Okay, so degree of k over f of alpha 1 into degree of f of alpha 1 over f. Okay, this one is n, which is equal to degree of k over f of alpha 1 into this one is r. So this implies degree of k over f of alpha 1, which is equal to n divided by r, which is less than n. Why? Because r is greater than 1, since I is greater than 1. Okay, so here the less than n by the induction hypothesis, the result is true. So here the k is normal extension of f of alpha 1 झालाय. We have to prove that k is normal extension of f na. Okay, so this implies now k is also splitting field of this f of x considered as a polynomial, over f of alpha 1. Okay, since the degree of k over f of alpha 1 is less than n. Okay, is less than n by induction hypothesis. Second step, the result is true for less than n. So by the induction hypothesis, capital K is normal extension of f of alpha 1. Okay, any doubt up to here? Okay.
No, sir.
Now we have to prove that the k is the normal extension of f. Okay. Wait a minute. As it turns out, k is also splitting field of f of x considered as the polynomial over f of alpha 1. Why? Because f of x तुमचा कशातला होता? f of x, but f is contained in f of alpha 1. Okay, give the reason. So here k is the splitting field of f of x considered as the polynomial over f of alpha 1, and k degree of k over f of alpha 1 is less than n. So by the induction hypothesis, k is the normal extension of f of alpha 1. Okay, now, but we have to prove that k is the normal extension of f of k is the normal extension of f. Okay, now let theta belongs to k be left fixed by every automorphism in GKF. In GKF. What is the meaning of this one? For every sigma belongs to GKF, sigma of theta is equal to theta. Okay. For every theta belongs to K, for every sigma belongs to GKF, we have sigma of theta is equal to what? Theta. Okay, let theta be the any element. Now, but we have one theorem. Which one? Wait a minute. Theta belongs to K. We left fixed by every atomorphism in GKF. So this implies what? Theta belongs to fixed field of GKF. Is it correct? So every sigma fixed this theta, then this theta belongs to what? Fixed field of GKF. Okay, fixed field of GKF means what? Take the collection of elements from the K, which leaves every sigma is belongs to this field. This group is fixed. Okay. Any doubt करते का मैं क्या समझता है? The theta belongs to K. आप प्रत्येक fixed by every atomorphism in GKF. That means this theta belongs to the fixed field of GKF. What is the field of GKF? Collection of all the elements from the k such that काय आहे definition काय आहे? Fix the field of GKF काय असतो हा set? X belongs to K such that sigma of X is equal to X for all sigma belongs to A के ना sorry wait a minute for all sigma X belongs to X काय असतो हा sigma of X is equal to X काय असतो the definition काय which leaves every element of F is fixed sigma for all sigma belongs to GKF yes.
GK.
Okay, so this is the definition of fixed field of GK. Take the elements from the K such that sigma of X is equal to sigma of X is equal to X for all sigma belongs to GK. Okay, so here the every automorphism in GK theta is fixed. That is sigma of theta is equal to theta. That means this theta belongs to what? Fixed field of GK. Okay, this is that. So this implies theta belongs to fixed field of GKF. Any doubt? Okay.
No, sir.
No, sir.
Now, wait a minute. Hmm. If we prove this theta is in F, then theta कशामध्ये गेलाय fixed field of GK. Okay, if we prove this theta is in F, then this capital F will be a fixed field of GKF. Okay, if we prove that theta is in F, then F will be the fixed field of GK, and we get K will be normal extension of capital F. Okay, is it clear? हा थीटा एक एलिमेंट घेतलाय K मध्ये जो every sigma from GK it left fixed. So this theta belongs to fixed field of GK. Okay, if we prove that this theta belongs to F, then we get F is contained in what? Fixed field of GK. Okay, एखादा एलिमेंट A मध्ये आहे तो एलिमेंट जर P मध्ये गेला okay X belongs to A. If we prove that X belongs to B, so what we get? B is contained in A. Okay, now this theta belongs to fixed field of GK. If we prove that this X, that means this theta belongs to the field F, then we get F is contained in fixed field of GKF. Is it correct? Any doubt?
Fixed field is
हो
contained
काय
in
म्हणताय?
F, na, sir.
एखादा एलिमेंट आहे okay if you take one element if X belongs to A, if we prove that okay if this X belongs to B ह्याच्यामध्ये जात असेल तर काय लिहितोय आपण sorry A belongs to B ना sorry A is contained in B. Is it correct? If X belongs to A
Yes, sir.
and if X belongs to B, then A is contained in B. So here the theta belongs to fixed field of GK. Suppose हा field तुमचा काहीतरी F dash असेल. Okay, आणि जर हा जर theta माझा F मध्ये गेला तर काय होईल? F dash is contained in F. Is it correct now? Okay.
Yes, sir.
Okay, so if we prove this theta is in F, then F will be the fixed field of GK, and K will be the normal extension of F by the definition. Okay, now we have let X sigma belongs to G G K F of alpha 1. Okay, what is the meaning of this one? Sigma leaves every element of F of alpha 1 fixed. Is it correct?
Yes, sir.
This implies sigma leaves every element of F is fixed. Is it correct? Since F is contained in alpha.
Yes, sir.
Okay, so this implies sigma belongs to G K F by the definition of this one. Okay, by this statement we get sigma belongs to G K F. Okay, so this implies by our assumption sigma of theta is equal to what? Theta. Since by our assumption theta is left fixed by every automorphism in GKF. Okay, what is theta? Chi theta upon theta. Theta belongs to K will left fixed by every automorphism in GKF. Okay, any doubt up to here? So here the sigma belongs to GKF, and by our
No,
assumption,
sir.
sigma of theta is equal to theta. Okay, now sigma of theta is equal to what? Theta. So this implies sigma of theta is equal to theta for all sigma belongs to G K F of alpha 1. Okay, why? On this one, sigma leaves every element of F of alpha 1 is fixed. Okay, so this implies theta belongs to fixed field of G A F of alpha 1. Okay, but we know that K is normal extension of F of alpha 1. Okay, on this one. And the K is the normal extension of F of alpha 1 here. Okay, so this implies F of alpha 1 is a fixed field of fixed field of G K F of alpha 1. Is it correct? If K is normal extension of F of. Okay, so this implies
Yes, sir.
theta belongs to F of alpha 1. Is it correct? ओके आता पहा थीटा घेतलाय
Yes, sir.
कुठून आपण आधी सुरुवातीला के मधून घेतला तो आलाय कुठे के बिलॉंग्स टू एफ ऑफ अल्फा इफ दिस थीटा बिलॉंग्स टू which one if this theta belongs to f then fixed field of gkf is contained in f. Okay, then we get our result. So theta belongs to here f of alpha 1. Now bracket alpha 1 is degree
R.
R over F ना, R over F. अल्फा वन ची डिग्री किती होती ते? अल्फा वन इज अल्जेब्राइक ऑफ डिग्री R over F. ओके, एकदा पुढे गेल्यानंतर मला लक्षात येत नाही म्हणून सांगतो, स्टेप बाय स्टेप समजून घ्या. Okay, if this theta belongs to f of alpha 1, what is the nature of f of alpha 1? We can write over here. We can write this theta is equal to lambda naught plus lambda 1 alpha 1 plus lambda 2 alpha 1 square plus up to so on lambda r minus 1 into alpha 1 raised to r minus 1. Okay, एकदम सुरुवातीला घेतला होता f of a चा नेचर कसा असतो? What is the nature of f of a? Beta naught
Beta naught
beta
plus
naught
beta
a
1
plus
A1.
beta naught a square up to so on beta 1, sorry, beta 2 up to so on beta n minus 1 a. All the betas are belongs
N
to
minus 1.
f na. So here all the lambdas. Here all the lambdas where lambda naught, lambda 1 up to so on lambda r minus 1 belongs to the base field f. Okay, हा जो field असेल ना ह्याच्यात नसेल. Okay, give it as an equation number 2. This is equation number 2. Okay, so by the previous theorem we get, what is previous theorem? By previous theorem, for each I running from 1 to up to so on R, okay, there is an automorphism. Okay, automorphism sigma I of capital K such that this sigma I belongs to G K F. Okay, such that sigma I belongs to G K F such that sigma I of alpha 1 is equal to alpha I. Is it correct? By previous theorem, for I running from 1 to R, there is an automorphism sigma I of K such that sigma I of alpha 1 is equal to sigma I, where this sigma I belongs to GKF. Okay. Any doubt?
No, sir.
Okay. Now, since theta is left fixed or leaves fixed by every automorphism in G K F. Okay, G K F. So this implies what? Sigma I of theta is equal to theta, and also also sigma I of theta is equal to theta, and also we have this lambda naught, lambda 1 up to so on this lambda r minus 1 are the elements of what? F. This implies sigma of lambda naught is equal to lambda naught. Sigma I of lambda 1 is equal to lambda 1 up to so on. Sigma I of lambda r minus 1 is equal to lambda r minus 1. Okay, each sigma I belongs to काय? तुमचा याच्यात नाही. Sigma I belongs to this one. Okay, so this is the automorphism of K, which leaves every element of F is what? Fixed. म्हणजे इथे here the lambda naught, lambda 1 up to lambda r minus 1 are the elements of F fixed. So each alpha I, okay, each sigma I of lambda naught प्रत्येक एलिमेंट काय होईल इथे पण फिक्स होईल. Why? Because lambda naught, lambda 1 up to lambda r minus 1 are the elements of F. Okay, any doubt? Now, operating
No, sir.
sigma I, operating sigma I on both sides of equation 2. What is equation 2? This one. Okay, so we get sigma I of theta is equal to sigma I of lambda naught plus lambda 1 alpha 1 plus lambda 2 alpha 1 square plus up to so on lambda r minus 1 alpha 1 raised to r minus 1. Okay, now sigma of theta is theta, which is equal to sigma I of lambda naught plus sigma I of lambda 1 into sigma I of alpha 1. Why? Because sigma I is an atomorphism plus up to so on. This is sigma of lambda r minus 1 into sigma I of alpha 1 raised to r minus 1. Okay, any doubt? Now,
No, sir.
theta is equal to, hence we get theta is equal to, this is lambda naught, this is lambda 1 alpha I. Sigma I of alpha 1 is alpha 1 na, so plus this is lambda
Alpha.
2. Sigma of alpha 1 square is nothing but alpha 1 square. Okay, sigma of alpha 1 ha असा येईल alpha square, that means alpha into alpha 1 into alpha 1, but this is an atomorphism, so sigma of alpha 1 into sigma of alpha 1, so alpha 1 into alpha 1 alpha square. Okay, so hence plus up to so on, this one is lambda r minus 1 and this is alpha 1 raised to r minus 1. What is the reason? Sigma I of alpha square, alpha 1 square is equal to sigma I of alpha into alpha, alpha 1 into alpha 1, which is equal to sigma I of alpha 1 into sigma I of alpha 1, which is equal to alpha 1 into alpha 1, which is equal to alpha 1 square. Okay, what is alpha 1? Correct. This is the reason. Now, so this implies lambda r minus 1 into lambda 1 sigma alpha 1 raised to r minus 1 plus lambda r minus 2 into alpha 1 raised to r minus 2 plus up to so on lambda 2 alpha 1 square plus lambda 1 alpha 1 alpha 1 plus lambda naught minus theta is equal to 0 for wait a minute, हवा का I theta is equal to I am. Okay.
I आहे sir.
Wait a minute. हा ऑपरेट केला I येईल ना इथे सिग्मा ऑपरेट केला. Sigma I of alpha 1 is there हा काय येईल alpha sorry but there is a there is an ह्याच्यावर sigma from this one sigma I of alpha 1 is equal to alpha. So here we get applying sigma on alpha 1, we get this is alpha. Okay, so this one is alpha. Okay, now this is the for I running from 1 to up to so on r na, give it an equation number third. Okay, since alpha 1 alpha 2 up to so on alpha r. All are distinct. All are distinct. Therefore, from equation number third, look at here. We see that hmm, the polynomial from equation third. Look at here. Q of x. Suppose that polynomial is q of x. Lambda r minus 1 into alpha r is to r minus 1 plus lambda r minus 2 into alpha r is to r minus 2 up to so on. This is lambda 1 of, instead of alpha, I write down here x. Okay, polynomial in x now. So this is x raised to r minus 1, x raised to r minus 2, and lambda 1 of x plus the constant term lambda naught minus theta. Okay, this is the polynomial of degree r minus 1. Okay, in k of x of degree at most degree r minus 1 has how many roots?
R minus
R roots. Is it possible? The degree of the polynomial of degree r minus 1, but it has r roots. Okay, look at here. For I running from 1 to r. Okay, म्हणजे इथे
no,
lambda
sir.
1 root आहे, lambda 2 root आहे, lambda 3 up to so on lambda r. These are the roots of this polynomial. Which polynomial? Q of x. But here the degree of q of x is what? R minus 1. So it is impossible to have a r root for a degree r roots of polynomial which has degree r minus 1. Okay, so this is the polynomial in k of x of degree at most r minus 1 has a r roots. Okay, instead of roots, write down distinct roots. In k of x of degree at most r minus 1 has r distinct roots. Okay, which one? Alpha 1, alpha 2 up to so on alpha r. So this can be possible. This can be possible only if all the coefficient of q of x are 0. Okay, so not 0 असायला हवा.
0.
What is the reason? Because the polynomial of degree r minus 1 cannot have r distinct root. Okay, so in particular, take the constant coefficient. What is constant coefficient? Lambda naught minus theta. Okay, so lambda naught minus theta must be 0. So this implies theta is equal to lambda naught. But what is lambda naught? Lambda naught belongs to f. Okay, look at here. All the coefficients are belongs to f. So here this theta must be element of f. Okay, since lambda naught belongs to f. Okay, any doubt? Hence,
No, sir.
इथे कुठून चालू केलं होतं आपण? Look at here. This theta belongs to fixed field of GKF. Look at here. Okay, now we get theta belongs to f. That means the fixed field of GKF is contained in what? Means the fixed
F.
field of GKF is contained in f. But we know that f is always contained in fixed field of GKF. Okay, हा always असतो. Fixed field of GKF. So this implies F is equal to what? Fixed field of GKF. Okay, so this implies K is normal extension of F. Okay, hence the proof. थीटा हा एलिमेंट मी कशासाठी घेतलाय? फिक्स्ड फील्ड ऑफ GKF इज कंटेन्ड इन F. हा स्टेटमेंट दाखवण्यासाठी हा थीटाचा उद्योग केला सगळा. ओके, थीटा बिलॉंग्स टू फिक्स्ड फील्ड ऑफ GKF. मग काय आला? थीटा बिलॉंग्स टू F ऑफ अल्फा 1 आला. Okay, by the nature of F of alpha 1, then the theta belongs to what? By using previous theorem, theta belongs to F. So from this we have this fixed field of GKF is contained in F. But in the last lectures, previous lectures, we seen that F is always contained in fixed field of GKF. From this both statement, we have F is equal to A is contained in B, B is contained in A. So A is equal to what? B. So here the fixed field of GKF is equal to F. So by the definition of normal extension, K is the normal extension of F. That's the proof. Any doubt?
No, sir.
Okay. प्रूफ थोडा लेंदी आहे, त्यामुळे सारखं वाचावं लागेल. एक प्रूफ एक थेरम 4-5 वेळा लिहून काढावं लागेल, त्यावेळेस तेव्हाच लक्षात येईल. Okay, so look at here. What is the statement? If field K is normal extension of a field F with characteristic 0, so normal extension असेल एखाद्या फील्डचा with characteristic 0, then K is a splitting field of some polynomial over F. Okay, any doubt?
No, sir.
Okay, so for today it is sufficient. Okay, the remaining part we will see tomorrow. Okay, अजून सिलेबस भरपूर आहे आपला. एग्जाम कधी आहे तुमची?